So Newton's first law tells us that any object in motion will remain in motion unless it's acted upon by a force, and an object that is at rest will remain at rest unless it's acted upon by an unbalanced force. Now, what is an unbalanced force? Remember before when we were talking about a skydiver jumping out of a plane? Initially, as he's accelerating towards the ground, he's accelerating because there's only a force acting downwards on him. But when he reaches terminal velocity, why are you laughing at me? When you reach terminal velocity, what happens with the forces? The force of gravity balances air resistance. So at that stage, you no longer have therefore at that stage you would have a balanced force when the gravity balances the air resistance. Now, some examples of where you might see Newton's first, some examples of inertia. So what is inertia? Inertia is basically an object's tendency to keep doing what it's doing. So that desk there wants to remain where it's moving, remain where it is unless a force acts on it. That's what we call inertia. A heavier object has more inertia than a lighter object. So some examples of where we see the effects of inertia in real life. If you're on a train and you're going pretty fast and then it was to stop suddenly, what does your body do? You jolt forward. Why? Because your body wants to keep doing what it was doing. Right, that's why if you're on a train and you're not holding on to something and the train stops suddenly, you're going to start moving because your body wants to keep doing what it's doing. It's currently in motion and wants to stay in that motion. The only thing that can stop you from doing that motion or stop that motion acting on you is if you grab onto something, because then you're applying another force on you to stop yourself. So when a train begins to move, your feet move forwards, but your body tends to remain stationary. So again, your body wants to stay in the same spot before you start moving. And then as the train starts moving, your feet are attached to the floor, therefore your feet start moving with the train, and then your body follows your feet. But if you were just hovering in the air and that train wasn't applying a force on you, then you would not move. Alright, this textbook was obviously before everything that's happening, because it's a little bit crowded. Alright, so that's Newton's first law, so we'll just make note of that in our books. So can you just note those two dot points, please? So Newton's first law states that, and then those two dot points. So now Newton's second law. An object will accelerate in the direction of an unbalanced force acting upon it. The size of this acceleration depends upon the mass of the object and the size of the force acting. So you don't have to copy this yet. I just want you to listen to what I'm saying. So if we consider this formula that they've included underneath, net force is equal to the mass times acceleration. So quite simply, that is a way that we can consider Newton's second law. The fact that force is equal to, or net force is equal to mass times acceleration. Now, if we apply a consistent force to two different objects, and one has a really large mass and one has a really small mass, would you expect their accelerations to be different? So if I apply a force to a truck, I try and push a truck with a certain amount of force, and then I try and push a bike with the same amount of force. Which one of those two would accelerate quicker? The bike. Alright, so if we consider this, so if the mass is really big and the force is constant, the acceleration is going to be small. Whereas if the mass is really small and the force is constant, then the acceleration is large. So for a constant force, so a good way to put this, I'll just I'll write the force being the same size in each of these. So we've got the same size force. if there's a small mass, the acceleration is going to be large. That's an A. And if we've got a large mass, the acceleration is going to be small. Not yet. So we can also rearrange that formula to determine, so if we know the mass of an object and the acceleration of the object, we can multiply the two to work out the force acting on it. So if we know a car's mass and we know a car's acceleration, multiply the two values and you'll know the force. What's force measured in again? Newtons. We can also rearrange Newton's second law in such a way that it's written as acceleration equals force over mass. And same type of thing, if you know a net force acting and you know the mass, and you can work out the acceleration. So here's another one of these triangles that you will need to use, or if you feel comfortable enough just rearranging that equation without copying that triangle out, that's fine as well. Alright, so just copy out now Newton's second law in words, and you can either copy this triangle or you can write F equals m times A, and you can do the rearrangements so then you know how we can use it to determine different quantities.